If you are a BARC interview aspirant in mechanical engineering, see this question. You have to draw the load versus X graph. This bar has a self weight and the gravity is acting downwards. Drawn it? Now see this question, I have added an external support on the bottom also. Now you have to draw the same graph. Can you draw it within 10 minutes without writing any equation? Can you draw it? Or even if you are writing any equation, that is okay, but you have to draw it within 10 minutes. So you can try it. And there are so many other possibilities that they could add to this single question. And there are other questions regarding strength of materials, like beams, like stress strain diagrams, which are having the same fundamentals that you have studied in your gate preparation, in your semester preparation, but the thinking process is different. The thinking way, the thinking habit is different, and we don't have generally that much thinking habit. And I also did not have that when I was appearing first time for the BARC interview. So I built that thinking process, and here in this course of strength of materials, I am also teaching you that how to build that thinking process and how to think when this type of question comes. So here is the sample of this video. First see it, then if you want you can buy it. So this course will actually cost you 899 rupees, 899, but for the next 24 hours, if you buy it within the next 24 hours, it will cost you 499, exactly half, right? And also there is a package. There is a package of heat transfer, fluid mechanics and strength of materials, which will total should cost you 899 into 3, but again for the next 24 hours it will be 499 into 3. But again there is a special discount if you are buying this package. Almost, already many people have already bought this, but for the next 24 hours I will only keep this offer valid, that you will get 499 into 2, and in that also you will be getting a discount of rupees 200. Okay, so see the sample. If you like it, then buy it or jane do. So this is a constant cross section area bar. Everything is same, but at maybe at any x. Okay, so at any x, so let me take that this is equal to L by 4 and the whole length is L, right? So we have a load P at at x equal to L by 4. We have a load P. Now you have to draw the load versus x. Now again here this is easy actually. We have to draw two free body diagrams, right? So for this one, if I draw the free body diagram here, then what will happen? Then let me just draw the section separately, right? Draw the section separately. Sorry. So here there will be two forces. One is the P, another is the weight, right? So they should be collinear. Let me draw it. This one, another is your weight, right? So this one, and this is your load F. So F will be equals to P plus weight. Now weight is a linear function of x, and now if I take a free body diagram here, here, okay, so this is for, maybe I will just name it, this is my cross section 1, this is also my cross section 1, right, and this will be my cross section 2, right. So this will be my cross section 2, and here I don't have any P, but now I have this one. This one is the weight and this one is F, right. So you see, for this one my F is only Wx. Okay, so if I now compare, if I try to compare, this is my F, this is my X. So at my x equal to L, the load is 0, and my x equal to 0, load is W, load is W for a constant cross section bar without any external load P. So let me just draw it here. So so this is without uh, without the load P, right? But now, but now, if I take a distance of x equal to L by 4, so this is this. Okay, so this is the x equal to L by 4, right? So this is x equal to L by 4. Now, see, from x equal to L by 4 to x equal to L, this free body diagram is valid, this free body diagram. So any cross section, if I take it here, if I take it here, what I have to do it, I have to take the cross section beyond this point, beyond x equal to L by 4, it will be W equal to, F equal to Wx. So it will follow this curve, it will follow this curve. So let me draw it, it will follow this curve, right? But so it will follow this curve, it will follow this curve, it will follow this curve. Okay, so there might be some breaks in video, I am sorry, because suddenly my iPad was shutting down, I don't know why. Okay, so this curve will be followed for x more than L by 2, and and before x equal to L by 2, sorry, before x equal to L by 4, for this section, for this cross section, this FBD will be followed. So F is equal to, obviously this will be there, but this will be shifted up by an amount of P. Okay, so maybe, okay, so for the actual case, at this, at x equal to 0, what will be my total load? P plus the weight of the rod. So this will be the case, P plus the weight of the rod, right? Total weight of the rod, okay, and it will decrease linearly up till this. So if I draw it like this, it will have a same slope and it will decrease. It will have a same slope and it will decrease. So this is my answer. If I just remove this, okay, or okay, I will not remove this. The blue colored is, so the blue colored is, okay, so with P. This is my blue colored one, right? With P. So you have to understand this concept. This is the concept of limit. So if I write at x equal to, so at, I mean when x tends to L by 4 plus, so it is approaching L by 4 from this side, it will follow this curve. And if there is, if I am approaching L by 4 minus, then it is approaching L by 4 from this side, from this side. So then it will be this curve. And here at x equal to L by 4, there is a discontinuity. There is a discontinuity. Okay. So this is the thing. So now can you draw the deflection also? Now can you draw the deflection also? Now the stress will be also exactly similar. Stress will be also exactly similar, right? It will be having a discontinuity here because the area is constant, so the stress will exactly follow this, and so will the engineering strain. But now what will be the deflection? What will be the deflection? So you see that that up till this part, up till this part, this P plus W is here, and here this was following the previous case. This was following the previous case. This was following the previous case. So here for these portions, for this portion, my slope of deflection. So this is again actually important. So let me explain it in details. In details. Okay. So what I can do is I can just, okay, I will draw it once more. So this is my x equal to L by 4, x, and this is my load, right? So this will be like this and this will be something like this. Okay, so you see that this is my force diagram. Now if I draw the load diagram by any other color, maybe I will draw it by green. I will draw it by green. So my deflection is drawn by green, delta. Okay, so maybe here I have some deflection. So will the deflection have any discontinuity? No. the deflection will not have any discontinuity in the value. It can have a discontinuity in the slope, and that we will see. Okay, so you will see that here from this point to this point the load is a bit more, it is decreasing in the same fashion, but the load is more, and if the load is more, some extra deflection will add to every point, at every point. So beyond this, so if I just color, sorry, what I am doing, let me just copy it, copy, and I will paste it here. So here if the load is more until this, okay, so the deflection will add up, deflection will add up to every point, deflection will add up to every point until this. Okay, so there you can see that there is a sharp increase. So let me draw the before curve. So okay, I will draw a separate curve for the deflection. Okay, so the deflection curve was looking like this, right? So delta versus x, at x equal to 0 deflection will be maximum and it will have an increasing slope. So this was your without p. Now with p what will happen? With p what will happen? So let us see, if I again draw that this is my x equal to L by 4, okay, L by 4, right? So this portion doesn't know, this portion beyond L by 4, this portion doesn't know that there is any L by 4, that there is a load, L by at x equal to L by 4. So this portion will exactly have the same slope, sorry, will exactly have the same slope, will exactly have the same slope, right? Will exactly have the same slope. So the slope will be exactly same. So the curve will be parallel to this. So the curve from this one to this one, it can either be this or this, but it will be exactly like this, exactly be parallel like this. Okay, but if I see here, for this portion, now you consider a case where there is no self weight, but a load at x equal to L by 4, that is P. There is no self weight, but there is a load at x equal to L by 4, and that is P. So then what will happen? Then what will happen? Then exactly a similar thing will happen, but now for P also. So if I draw for P only, so if I draw for P only, it will be again something like this. Okay, it will be again, maybe it will be something like this, maybe. Okay, maybe it will be something like this, right? Maybe it will be something like this. So if I just add these two, so this is only P, this is only P, so no self weight, this is only P. So and this is, and this is, or I should write here only self weight without P, and this is only self weight, SW. So only self weight plus only P, only self weight plus only P. Now you can see that this P graph can be like this also, sorry, this P graph can be like this also, can be like exactly same like this also, can be like this also. Okay, this we cannot know, okay, if we don't have the exact I mean if we don't have the exact analysis, right? So here you see that if this is your P and this is your only self weight, we can linearly superpose them, and maybe now this will be my graph, and from this point, it will have an exact variation like this, So what we can do is, you just take this much distance and you cut a same distance like this and you just draw it here, the same curve, sorry, the same curve. So what I can do is, I will show you, I will just cut this much curve, I will just copy it and I will just paste it here, maybe, yeah, this much curve. It is not showing up like this. So what I am trying to show you is this. Let me show you that, see, this is same curve, the exact parallel curve will be here, the exact parallel curve will be here. So let me draw it very calmly, exact parallel curve, or maybe with another color here, with this one, so this one, okay. So this one will be the curve, right? This one will be the curve. See, deflection cannot be linear, deflection cannot be linear even with a constant load, even with a constant load. Why it cannot be linear? Because of this two friend one friend logic, two friend one friend logic that I have shown. This one, this one logic. Deflection cannot be linear. Even if the strain is linear, the slope is linear, deflection cannot be linear. So in that sense here the stress is constant, and I mean for this case only, for this only load P, only P, until this one, until this section, the load is constant, the stress is constant, and the engineering strain is also constant. Okay, engineering strain is also constant, but the variation of deflection cannot be linear for that reason. Okay, because this section will have some delta on, and that will add up to this section. Okay, okay. And actually for P only case, this section will not have any stress, any load, any strain. Okay, so this will just add up linearly. I mean this will just add up linearly, or this will be just constant. Okay, but now what I am trying to say is this will be exactly same. Okay, this will be exactly same, this will be exactly same, this deflection. Okay,